Hi, we are discussing theorem 8.7. The null statement the function e of z. In order to discuss e of z is the series that is periodic with period 2 pi I. The second statement is the function c and s. We have defined this c of x and s of x in terms of e of z. Those are also periodic with period 2 pi. This is 2 pi I and this is 2 pi. This is the second statement. Third statement, if we choose any t in between 0 and 2 pi, then this e never assume 1. That is the third statement. E of it എന്ന് പറയുന്നത് ഒരിക്കലും 1 ആവില്ല എന്നുള്ളതാണ് മൂന്നാമത്തെ statement. In this interval, 0 less than t less than 2 pi. If z is the fourth statement is if z is a complex number with mode z equal to 1, then there is a unique t belongs to closed 0 open 2 pi such that e of it is equal to z. Okay. ഈ പറഞ്ഞ ഇന്റർവെല്ലിൽ നിന്ന് കോംപ്ലക്സ് പ്ലെയിനിലേക്ക് ഒരു ഫംഗ്ഷൻ ഡിഫൈൻ ചെയ്യുകയാണെങ്കിൽ ഇ എന്ന് പറയുന്ന ക്യാപിറ്റൽ ഇ എന്ന് പറയുന്ന ഒരു ഫംഗ്ഷൻ ഡിഫൈൻ ചെയ്യുകയാണെങ്കിൽ ഈ ഫംഗ്ഷൻ ഇസഡ് ഈ പറഞ്ഞ ഇ ഓഫ് ഐ ടി എന്ന് പറയുന്നത് എന്താ പറയാ 1 ആയിരിക്കും, അല്ലെങ്കിൽ അത് ഇസഡ് അറ്റൈൻ ചെയ്യുന്ന ഒരേ ഒരു പോയിന്റ് മാത്രമേ ഈ പറഞ്ഞ ഇന്റർവെല്ലിൽ ഉണ്ടാവുള്ളൂ എന്നുള്ളതാണ്. അപ്പോൾ വേണമെങ്കിൽ ഇ ക്യാൻ ബി കൺസിഡർഡ് ആസ് എ 1 and 1 ഫംഗ്ഷൻ ഫ്രം ദിസ് interval 0 to pi to mod z equal to 1, set of all z such that mod z equal to 1 എന്ന് പറഞ്ഞ് നമുക്ക് കൺസിഡർ ചെയ്യാൻ പറ്റും. 1 1 2 ആയിരിക്കും എന്നുള്ളതാണ് ഈ സ്റ്റേറ്റ്മെന്റിന്റെ കോൺസിക്വൻസ് ആയിട്ട് നമുക്ക് പറയാൻ പറ്റുക. ഓക്കെ, അപ്പോൾ ഇത് ആദ്യത്തെ സ്റ്റേറ്റ്മെന്റ് ഓൾറെഡി നമ്മൾ കഴിഞ്ഞ ദിവസം പ്രൂവ് ചെയ്തതാണ്. ഇ ഓഫ് z is periodic. That is because of this e raised to e of 2 pi I എന്ന് പറയുന്നത് 1 ആണെന്ന് നമ്മൾ പ്രൂവ് ചെയ്തിട്ടുണ്ട്. So we can easily prove that e of z plus 2 pi I. E the property, capital E the property basis e of z into e of 2 pi I എന്ന് വിളിക്കാം. So that will give e of z itself. First statement the proof. Second statement, so this is the proof. Proof the second statement is the functions c of x and s of x are periodic with 2 pi. For that we consider c of x plus 2 pi. We will prove that c of x plus 2 pi and s of x plus 2 pi are same as c of x and s of x respectively. That we prove here. So we start with this one, c of x plus 2 pi and plus I times s of x plus 2 pi. This is in fact e of I x plus 2 pi. C of x and s of x in a definition which is some kind of property result. So this can be written as e of I x plus I times 2 pi. And at the ID usual a part of usual, this can be written as e of ix because 2 pi I is the period of this capital E. What is e of ix? E of ix is c of x plus I s of x. So when the real part imaginary compare c of x plus 2 pi equal to c of x and s of x plus 2 pi എന്ന് പറയുന്നത് s of x എന്ന് പറയും. രണ്ടും കോംപ്ലക്സ് നമ്പേഴ്സ് ആണെങ്കിൽ കോംപ്ലക്സ് നമ്പേഴ്സ് ഇക്വേറ്റ് ചെയ്യും, റിയൽ പാർട്ട് ഇക്വേറ്റ് ചെയ്യാം, ഇമാജിനറി പാർട്ട് ഇക്വേറ്റ് ചെയ്യാം. ഓക്കെ, സോ ദാറ്റ് ഇസ് ദ പ്രൂഫ് ഓഫ് second one. For the third one we will consider the interval 0 less than t less than 2 pi. ഓക്കെ, ഇതിനകത്ത് ഇ ഓഫ് ഐ ടി 1 അറ്റൈൻ ചെയ്യില്ലെന്നാണ് കാണിക്കേണ്ടത്. അപ്പോൾ നമ്മൾ ചെയ്യുന്നത് ഇഫ് വി കൺസിഡർ 0 ലെസ് ദാൻ ടി ലെസ് ദാൻ പൈ ബൈ 2 ഫസ്റ്റ്. ഓക്കെ, ഇഫ് യു കൺസിഡർ ദിസ് ഇന്റർവൽ ഫോർ ദ ടൈം ബീയിങ് forget about this interval, so you consider e 0 less than t less than pi by 2, and we will later consider e of 4it. Okay, so when this t varies over this interval, e of 4it will give the values of e of it where t varies over the original interval. That t 0 to 2 pi vary ചെയ്ത് കിട്ടുന്ന e of it തന്നെയായിരിക്കും 0 less than t less than pi by 2. t 0 to pi by 2 vary ചെയ്ത് കിട്ടുന്ന e of 4it യുടെ വാല്യൂസ്. ഓക്കെ, അത് കിട്ടാൻ ജസ്റ്റ് സബ്സ്റ്റിറ്റ്യൂഷൻ മാത്രം നടത്തിയാൽ മതി. ഇപ്പോൾ ഈ പറഞ്ഞ ഈ പവർ ഐ ടി നമ്മളൊരു 4 times സം ഐ യു എന്ന് റീപ്ലേസ് ചെയ്ത് കഴിഞ്ഞാൽ you can get e of 4iu is same as e of it is same as e of 4iu with the substitution of it is equal to I times 4u. Then this can be written as 0 less than u less than 2 pi. This is in fact 4u, so we can write 4 here, so that will give pi by 2. But then the same values assumed by this E എന്ന് പറയാൻ പറ്റും. അല്ലെങ്കിൽ B പ്രൂവ് ചെയ്യുന്നതിന് പകരം നമ്മൾ എന്ത് പ്രൂവ് ചെയ്താൽ മതി? E of 4IT never be 1 for t values over this. Okay, അപ്പോൾ അതാണ് നമ്മൾ പ്രൂവ് ചെയ്യാം. അപ്പോൾ അത് നമ്മൾ ചെയ്യുന്നത് we will consider E of IT as a complex number, so that is equal to x plus iy. In fact, this x is c of something, c of t, and y is s of t. Okay, if you write like this, then we know that E of IT is c of t plus I s of t. Okay, so from this you can get this c of t is this x and s of t is this y. Okay, അപ്പോൾ E of IT നമ്മൾ എക്സ് പ്ലസ് ഐ വൈ എഴുതി കഴിഞ്ഞാൽ ഇവിടെ നമുക്കറിയാം എക്സും വൈയും നമ്മൾ കൺസിഡർ ചെയ്യാൻ പോകുന്നത് E of IT 1 വരുന്നുണ്ടോ എന്നുള്ളതാണ്. സോ ഹിയർ ദിസ് ഫ്രം ദ ഡെഫിനിഷൻ ഇറ്റ്സെൽഫ് ദീസ് ടു ക്വാണ്ടിറ്റീസ് ആർ real part and imaginary part of this complex number, so those values are x and y are real, and we have already discussed that c of t starts from this, that is c of 0 is 1, then this is the first this pi by 2, this is the pi by 2 is the first 0 of this c of t as far as positive values are concerned. So we know that in this interval 0 to pi by 2 our c of t are always positive, and we already, this is c of t, and we know that s of 0 is 0, and s of t is increasing throughout this pi by 2, so we know that this is the graph of s of t. So this s of t and c of t are all positive as far as this interval is concerned, 0 less than t less than pi by 2. So we can say that this x and y are real positive. Okay, so these are the not only positive, these values lies in between, this is in fact 1, so these values lie in between 0 and 1, therefore this x and y. So 0 less than x less than 1, 0 less than y less than 1. ഇതാണ് ഈ ഇന്റർവെൽ. 0 c of t എന്ന് പറയുന്നത് 1 ആയിരിക്കും, s of t എന്ന് പറയുന്നത് 0 ആയിരിക്കും. പക്ഷേ ഓപ്പൺ ഇന്റർവൽസ് കൺസിഡർ ചെയ്താൽ ഈ എക്സും വൈ എന്ന് പറയുന്നത് 0 1 ഇൻ ബിറ്റ്വീൻ ആയിട്ടുള്ള രണ്ട് ക്വാണ്ടിറ്റീസ് ആയിരിക്കും. ഓക്കെ, അതുകൊണ്ട് തന്നെ ഇഫ് യു ഇവാലുവേറ്റ് E of 4IT that is equal to x plus we know that this E of 4IT is as E of IT into E of IT into E of IT 4 times, so this can be written as raised to 4, that is equal to x plus iy whole raised to 4. By simplifying this you can get it expand here in the real part, imaginary part group here. Okay, then you get x raised to 4 minus 6x square y square plus y raised to 4 plus 4ix y times x square minus y square. So we are searching for t such that E of 4IT is equal to 1. That means this right side should be 1. That means the imaginary part should be 0. So we are searching for t such that the imaginary part should be 0 and this quantity is 1. Okay, that is the problem C. So we by equating the imaginary part equal to 0, you can get this x square minus y square equal to 0. Okay, whenever this x equal to 0, x equal to 0, y 0, we can get all these quantities are 0, so we can never expect that x equal to 0 and y is equal to 0, and x equal to, if we assume x equal to 0 and if you get this from this you can get 3 possibilities: x equal to 0 or y equal to 0 or this one, x square minus y square is equal to 0. But we can rule out these two possibilities, because whenever x never be 0 anyway, this is x and y lie in between 0 and 1. So we can expect the only possible condition is x square minus y square is equal to 0, and we have x square plus y square is equal to 1, because this x and y are the real parts of this E of IT, and we know that modulus of E of IT is equal to 1, that we have discussed in the previous theorem. Previous discussion. So this can be, from these two statements we can get to this x square equal to y square is equal to half, and hence by solving this you can get this one, and hence we can get E of IT for IT is equal to minus 1. Okay, x square y square എന്നുള്ളത് ഹാഫ് ഈ പറഞ്ഞ ഇക്വേഷനിൽ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് കിട്ടും ഈ പറയുന്ന E of 480 എന്ന് പറയുന്നതിന്റെ പോസിബിൾ വാല്യൂ ഇതാണെന്നുള്ളത്. ദാറ്റ് മീൻസ് ഓൺലി പോസിബിൾ റിയൽ വാല്യൂ assumed by this E of 480 is minus 1. Okay, that means this E of 480 never be 1 for 0 less than t less than pi by 2. അതിൻ്റെ അർത്ഥം ഈ പറയുന്ന E of IT നമ്മുടെ അടുത്ത സബ്സ്റ്റിറ്റ്യൂഷൻ ഉപയോഗിച്ച അനുസരിച്ച് E of IT എന്ന് പറഞ്ഞ ഈ ഇന്റർവൽ ഒരിക്കലും 1 അറ്റൈൻ ചെയ്യില്ല എന്നുള്ളതാണ് നമുക്ക് ഇവിടെ കൺക്ലൂഡ് ചെയ്യാൻ പറ്റുന്നത്. So next we have D part. D part says that if Z is a complex number with mode Z equal to 1, there is a unique t. ഓക്കെ, അതായത് ഏത് കോംപ്ലക്സ് നമ്പറും മോഡൽസ് 1 ആയിട്ട് എടുത്താലും നമുക്ക് ഒരേ ഒരു ടി എ ഈ ഇന്റർവെല്ലിൽ കണ്ടെത്താൻ പറ്റുള്ളൂ. ഇത് 0 ലെസ് ദാൻ ഓർ ഈക്വൽ ടു ടി ലെസ് ദാൻ 2π ആണ്. ഇവിടെ ഓപ്പൺ ഇന്റർവെല്ലാണ്, ഇത് ക്ലോസ്ഡ് 0 ആണ്. ഓക്കെ, അപ്പോൾ നമ്മൾ വി സ്റ്റാർട്ട് വിത്ത് ഫോർ ഡി പാർട്ട് വി സ്റ്റാർട്ട് വിത്ത് കോംപ്ലക്സ് നമ്പർ ഡി. സോ if you choose this is the complex number z such that we choose let z belongs to C such that mod z equal to 1. Okay, അത് നമ്മൾ ഇതിന്റെ യൂണിക്നെസ് പാർട്ടാണ് ആദ്യം പ്രൂവ് ചെയ്യുന്നത്. അതായത് ഇപ്പോൾ E of IT എക്സിസ്റ്റൻസിനേക്കാൾ മുന്നേ E of IT എവിടെയെങ്കിലും z അറ്റൈൻ ചെയ്താൽ ഇങ്ങനെയുള്ള ഒരേ ഒരു z ഉണ്ടാവുള്ളൂ എന്നുള്ളതാണ് നമ്മൾ ആദ്യമേ പ്രൂവ് ചെയ്യാൻ പോകുന്നത്. ഓക്കെ, അപ്പൊ അതിന് വേണ്ടിയിട്ട് നമ്മൾ ഏതെങ്കിലും രണ്ട് ടി 0 ലെസ് ദാൻ ഓർ ഈക്വൽ ടു T1 ലെസ് ദാൻ T2. So suppose there are two distinct values for t such that from this interval such that E of IT equal to E of IT1 is equal to E of IT2 is equal to Z. ഇങ്ങനെ ഏതെങ്കിലും രണ്ട് വാല്യൂസിൽ ഡിസ്റ്റിങ്ക്ട് വാല്യൂസിൽ Z അറ്റൈൻ ചെയ്തു എന്ന് വിചാരിക്കാം. അങ്ങനെ സംഭവിക്കുന്നതാണ് E of IT2 into E of IT1 whole to the power minus 1. That is this one. ഇങ്ങനെ രണ്ടും ഈക്വൽ ആയി കഴിഞ്ഞാൽ ഇതിന്റെ പ്രോഡക്റ്റ് എന്തായിരിക്കും? ഓക്കെ, ഇതിന്റെ പ്രോഡക്റ്റ് 1 ആണ് വരേണ്ടത്. Because if these two are equal, then this product should be 1. But when you consider this one, we can get E of IT2 into E of നമുക്കറിയാം E of IT1 whole to minus number minus IT1 ആണ്. നമ്മൾ ഡിസ്കസ് ചെയ്തിട്ടുള്ളതാണ് E of EZ into E of minus z എന്ന് പറയുന്നത് 1 വരും എന്നുള്ളത് നമ്മൾ നേരത്തെ ഡിസ്കസ് ചെയ്തിരിക്കുന്ന കാര്യമാണ്. സോ യൂസിംഗ് ദിസ് ഫാക്ട് ദാറ്റ് മീൻസ് E of minus z is 1 by E of z, that is E of z whole to minus 1. അത് ഉപയോഗിച്ച് കഴിഞ്ഞാൽ നമുക്ക് ഇങ്ങനെ എഴുതാം. So this can be written as E of IT2 minus T1. By comparing these two, you can get this one, and this is E of this is equal to 1. Okay, but this is a contradiction. Okay, so when you get this one, 1 is equal to E of I times T2 minus T1. Okay, what is the property of this T2 minus T1? T2 minus T1 is always greater than 0 because this T2 is greater than T1, and T2 minus T1 never be 2π. Okay, because these two values are in between this 0 and 2π, so this distance will be always less than 2π. So from this you can get T2 minus T1 which is in between 0 and 2π such that E of I of that quantity equal to 1. Okay, so this is a contradiction. This statement is a contradiction because we have already proved that in the C part this never happens. Okay, from this you can write E of IT is equal to 1 for 0 less than T less than 2π. Okay, so this is a contradiction. So what is T is equal to T2 minus T1. So this is a contradiction due to the part C. So we can get the uniqueness. So this never happens. We can never expect two distinct values T1 and T2 such that E of IT1 and E of IT2 are the same Z. Okay, so this proves the uniqueness part of the fourth statement. Okay, now we'll prove the existence part with this. Let Z belongs to Z complex numbers and mod Z is equal to 1. Okay, so write Z is equal to x plus iy with x and y are real y are reals. Suppose that first of all we consider the possibilities of this x and y are x is greater than 0 and y is greater than equal to 0. That means if you are considering z lies on the first quadrant of the complex plane. Okay, if you choose such, we know that we are considering all z with modulus value is 1. Okay, so that means we are considering only the unit circle in the complex plane. So first of all we consider all the z in this part. Okay, that's the meaning of this. Okay, if you consider any z in this segment, then we can, that is the meaning of this one, x greater than equal to 0, y greater than equal to 0. Then we can get on 0 pi by 2. When you consider this interval 0 pi by 2, we know that c decreases. Okay, we already discussed what is the properties of this c in the interval 0 pi by 2. So the c is nothing but c starts from this point. At 0 we have 1, this graph of c of t, and it decreases to 0. Okay, at the point pi by 2 we can get the c of t is equal to 0. Okay, now the c decreases from 0 to 1, sorry 1 to 0, 1 to 0, hence c of t equal to x for some t. Okay, some t. That means if you consider this one, if you consider any x greater than or equal to 0, then if you choose any x greater than or equal to 0, then when you consider y equal to x here, okay, that this cuts. That is not a line. If you consider any x here, then you consider a straight line passing through this x. Okay, then we can say that this x is in between 0 and 1. So this x, when you consider this x and consider the line t is equal to x here, then we can get, since this is decreasing, then we can get at least one point at which this curve of c of t intersect with this line. Okay, so if you choose that point, I will mention that graph here. Suppose this is the graph of c of t. Okay, if you consider any x in between this 0 and 1, then you consider a straight line passing through this point x, then you can easily get a point t here in between this 0 and pi by 2, or in the interval 0 pi by 2, such that c of t is equal to x. And at this point we can get c of t is equal to x. That means since the c decreases from 1 to 0, hence c of t equal to x for some t in between, some t in the interval 0 pi by 2. Okay, so we choose that one, and we know that c square plus s square is equal to 1, and s is always greater than or equal to 0 in this interval. S is like this. The graph of s is like this in this interval. So since s is greater than or equal to 0, we can get from this equation you can get this s square is equal to root of 1 minus c square. That means s equal to root of 1 minus c square itself. Okay, so this s is 1 minus c square, then s square is 1 minus c square, then s is equal to root of 1 minus c square. Since this is positive, we know that this value is root of 1 minus c of t. Okay, c of t is equal to x, then we can write s of t is equal to this value. Okay, s of t can be written as root of 1 minus x square. Since this s is positive here, then we can get this e of it corresponding to this t. We know that e of it is equal to c of t plus I s of t. We know that this quantity is equal to e of it. So that is equal to, what is c of t? C of t is x, and we put this value is y. Okay, and this will be x plus I y. Okay. Okay, so this shows that for any z in between the 0 and pi by 2, sorry, any z equal to x plus I y such that x is greater than 0 and y equal to greater than 0, we can get a point t in between 0 and pi by 2 such that p of I t is equal to x plus iy. Okay, so we already proved that the uniqueness, so we can get the expressions for this first quadrant. Okay, now we consider the second quadrant. If x is less than 0 and y is greater than or equal to 0. Okay, we are considering this part. Okay, when you consider this part, x is less than 0 and y is greater than 0, and then we consider this is x plus iy, and x is less than 0 and y is greater than 0. In this case, we put w is equal to I minus iz. Okay, then what will be this w? This w will be minus I times x plus iy. So that will give this y minus or y plus I times minus x. Okay, so that is the value of this w. Since the y is greater than or equal to 0 and this x is less than 0, this minus x is greater than 0. Okay, so we can say that this x and y satisfies the previous condition, or this quantity. This implies w belongs to the first quadrant. Okay, then we already proved that whenever we choose a point z in the first quadrant, we can easily get the segment from the first quadrant, we can get t such that. Okay, so using the previous discussion, we can get a t such that the axis t belongs to the interval 0 pi by 2 such that this pi by 2, this here we can assume open interval because we are not considering x equal to 0, so we can get a point from 0 pi by 2 such that, or first of all we can write like this, such that e of it is equal to w, since this w lies on the first quadrant. Okay, so since this e of it is equal to w, which is equal to minus iz, without substitution, this is minus iz, then we know that this I is equal to this I can be written as e of minus I can be written as e of I pi by 2. Okay, we know that e of I pi by 2 is minus 1, that we already discussed, that is z into z. Okay, now you combine this two, or transposing this e of I pi by 2 t to the left hand side, we can get z is equal to e of I times t plus pi by 2. Okay, we know that t lies in between 0 and pi by 2. Okay, what happens when t is equal to pi by 2? That is the next condition. If t is equal to pi by 2, then what is e of what is that z? This e of it is equal to c of e of pi by I pi by 2 is equal to e of pi by c of pi by 2. So that can be written as, we write it as e of I pi by 2, this is equal to c of pi by 2. C of pi by 2 is equal to 0, and we know that this is minus this is I. Okay, so this is the value of e of I pi by 2. So when this t is equal to pi by 2, the value of this e is equal to I. Okay, so that that is what we have substituted here, and now we have z is equal to e of this is t plus pi by 2, and this t lies in between this 0 and pi by 2. Now what happens to this t of t plus pi by 2? So we know that this t plus pi by 2 lies in between 2 pi and pi by 2. Okay, when you add pi by 2 to this interval, you can get t plus pi by 2 lies in between this. Okay, so we have for any z satisfying this, you can get e of I times t plus pi by 2 such that where this t plus pi by 2 satisfies this condition. Okay, so this proves the second part. Whenever we have x less than 0 and y greater than or equal to 0, we have x and y, sorry, we have value t plus pi by 2, that quantity lies in between this interval such that e of this quantity is equal to x plus iy. Okay, so this proves the case when z lies in the segment from the second quadrant. So now we have proved that whenever we consider the circle, unit circle, and if we choose any points from this part, z, we can get the axis t belongs to this interval 0 to this pi. 0 to this pi. We already proved that this value is in between. Also, this is not 2 pi, this is in fact pi by 2 plus pi by 2. So this is pi. This is not 2 pi. When we add pi by 2 to this inequality, we can get pi by 2 less than t plus pi by 2 less than or equal to pi by 2 plus pi by 2, that is pi. So we can get from this interval, for any t belongs to this, then any z belongs to this segment, the axis t belongs to this such that e of it is equal to z. Okay, so that is the previous discussion. Now we consider the case z equal to x plus iy and y is less than 0. That means if we choose any z from this part, okay, we will consider these two segments together. Then if we choose any w from this part, we can get that or we not w, this is z, any z from this part, then you consider minus z, or put w is equal to minus z. Okay, so if z is equal to x plus iy, then this will be minus x plus I times minus y. So this belongs to the first part. Okay, this belongs to the first two quadrants, first or second quadrant. First or second quadrant. So we already proved that whenever we have any z from the first or second quadrant, if we have w here, then we can get this t. So the axis t belongs to 0, pi, such that e of it is equal to w. Okay, but we know that this w is equal to minus z. Then this minus z can be written as minus this, we write that minus 1 into z, and this minus sign, this minus 1 can be replaced by e of I pi. Okay, this minus 1 can be replaced by this, then z will be, by transposing this e of I pi to the left hand side, then z will be, z can be written as e of I, this is e of minus I pi, so we have e of I times t plus pi. Okay, so this is because we know that minus 1, e of minus I pi can be written as c of pi plus I of s of pi. Okay, we already proved that this quantity is minus 1 because of the c of pi is equal to minus 1 and s of pi is equal to 0, so we can get this is minus 1. So we replace this minus 1 by e of minus I pi, and you transpose this to this, okay, left hand side. So e of it divided by e of minus I pi, that is e of I pi. Okay, 1 by e of minus I pi is e of I pi, so we can write z is equal to this. But we know that this t plus pi, this t lies in between 0 and pi, then t plus pi belongs to this pi to 2 pi. Okay, so we can in each case we have t such that e of it is equal to z, and that t belongs to 0 to 2 pi. Okay, so this proves the fourth statement of the theorem. Okay. Now, after this theorem, there is some discussion about the curve gamma of t. If we define gamma of t is equal to E of it in the interval 0 less than or equal to t less than or equal to 2 pi. Okay, as a consequence, we can get gamma dash of t is equal to I times E of it. Then the length 0 to interval 0 to 2 pi mod gamma dash of t, that will give the length of the curve. Dt is equal to 2 pi. Okay, using this fact you can prove this one. So using this you can easily prove that this C of t and S of t satisfies all the properties of the trigonometric functions cos t and sin t. So in fact these two quantities are not only the series representations. We already proved that the C of t is equal to E of it plus E of minus it by 2, and E of it minus E of it minus it divided by 2i. We have defined the C of t and S of t in means of these power series, but after this, by using this fact, you can easily identify the C of t and S of t as our usual trigonometric functions cos t and sin t, due to this, because this gives the perimeter of the unit circle, and that is discussed in one or two paragraphs after this theorem. So please go through it. In the next class, we will discuss the algebraic completeness of complex fields. That means the fundamental theorem of algebra, using these ideas of these functions that we have discussed. Okay.